Hello, prisoners. The first unit that we're going to work through is all about the functions that you learned about in Algebra 2, as well as their potential transformations. Now, in all technicality, this unit is supposed to be reviewed since all of these functions should have been covered in your previous classes at some point. But a lot of things should have happened last year. Some people should have gotten married. Some people should have seen their families on holiday. Some people maybe just want to see live music again. So, it's worth covering again from the beginning. So while I get to the skills and the techniques and everything in a little bit, let me take some time first to explain what you're doing here. I can't guarantee you'll find it important, but I can, still just tell you anyways. Function unit is all about understanding the concept of mathematical patterns. When you think of a pattern, the imagery is usually a sequence of repeating numbers or letters or maybe like a symbol or shape. Perhaps you have a sequence of numbers that isn't necessarily repeating, but is changing in such a way that you would always know the next number no matter where you were in the pattern. For example, if I show you this pattern of 5 numbers, then ask what number would go next after, say, the number 22, you would probably guess that the answer is 24, since the first 5 numbers were all increasing by 2 with each step in the sequence. This generalizes the idea of a pattern to any sequence where the next step is predictable. When it comes to numbers, there's an infinite amount of patterns you could employ, counting up or down by however much you want at a time. But all these patterns are doing essentially the same thing. What about this pattern? These numbers aren't going up or down by the same amount between any step, so how could this still be seen as a pattern? The answer is multiplying. Each number is twice as large as the number before it in this sequence. Since there's an infinite amount of numbers that you could multiply or divide by, we now have 2 finite, infinite pattern categories. Try to make sense of that, but I'd suggest having a mop handy for when your brain leaks out of your ears. Maybe it would be easier to think of these 2 infinite pattern sets as functions, because that's a smaller, not as scary sounding word. What other less scary functions are out there? Well, how many different ways can we manipulate a number? We've already talked about adding, subtracting, multiplying, and dividing, but we could also take a number to a power like a square or a cube, use a square root or other type of radical, take a logarithm or a sign of a number, or flip the number into its reciprocal. These are all the different types of functions that can generate their own unique patterns, and they all got some little names, and they all they got different shapes when you make them into pictures, and that's about it. That's really the whole point of this. A function can be expressed in 4 different ways. The first thing you can do is describe the pattern in words like we've been doing. Here's a list of words that can convey the meaning of each of our patterns as simply as possible. If you're writing it down instead of talking, it's probably faster to write out the function algebraically, meaning that you use math symbols and stuff like that. Here's what each of these functions look like as expressions. If you want to make these equations more proper, you can make them equal to this symbol, which is called f of x, short for function, where x is the variable. Another great mathematical way a function can be shown is through a table of values. This can be made by writing out a number of steps to the pattern and its result. These are more detailed than the previous 2, since multiple steps are required for someone to be able to guess the pattern that they're seeing, though with enough steps and a simple enough pattern, sometimes you can even skip over steps and the pattern's still easy enough to see. Last, we have graphs. Graphs take patterns and turn them into pictures. That's great. It sounds like something you might do on like a kid's show. Like a kid's craft show or something. I don't know. Look, I'm just jealous I didn't get to grow up with Yo Gabba Gabba. Do you have any idea how lucky you are? To make a graph of a function, you plot a series of points, which we call coordinates, on the graph, each having a horizontal and vertical position determined by the inputs and outputs of the pattern. When making a graph, it's almost always easiest to start off by making a table of values, then turning the table of values into coordinates on the graph. It's also a good idea to list the table of values with your graph, so your reader, aka me, can interpret your graph better, since some of you have, mid-penmanship. I'm sorry, I'm saying it, it's true.
Brain blast.
Did you think of this? What if I take this pattern of counting by 2s, but I list it like this? You could say I'm counting by odds, or still just say I'm counting by 2s, but most people wouldn't start in the same place as me if they were told to copy my pattern with just that information. you'd need to tell them something like count by 2s starting at 5. When you change a detail of a pattern without fundamentally changing the pattern itself, you are transforming the pattern. Transforming a function changes the positions or the dimensions of the points on the function's graph as well. Adding or subtracting numbers to a function in different places will shift the graph that many points up, down, left, and or right. Multiplying parts or all of the function will dilate it, causing it to stretch or shrink vertically and or horizontally. The functions can also be reflected by making part or all of the function negative, and inverted by switching the input and output values in the coordinates of the function. It's possible for multiple or even all of these transformations to take place on any of these functions, though some are not as easy to be seen in the visuals of the graphs. Also, notice that none of these graphs look that different from their regular versions, which we call parent functions. Think of transformations like you would do to an image in Photoshop. You can move the image around, stretch it or shrink it, you can flip it over and even invert it, but it's still the image you put into Photoshop in the first place, just a different version of it. Same energy here. So that's it. That's the concept of functions as mathematical patterns explained. And now you can transform them. That means we know all of it, right? So we don't really have to like work on it, right? I mean, you could just like go back and watch this video again if you forget about it, right? It's not like there's like any purpose to doing busy work to just drill this fairly plain and shallow concept into a At least we have technology to ease the pain of repetition ad nauseum. Here's one of our functions, x squared. Here it is, shifted up by some amount. Here it is, shifted up and to the right. Here it is, shifted up, right, and stretched vertically. Here it is with a horizontal stretch applied as well. The resulting expression here is called the general form of the function, which has all the possible placeholders for numbers that would cause a transformation as opposed to the parent form, which has none of these. It turns out that the general form of functions is nearly the same in each function, with the placeholder values in relatively the same spots, always doing the same things to the function they're in. If we put one of these general forms into Desmos' graphing calculator, we get sliders that allow us to adjust the values of the placeholders to see how transformations change the position, dimensions, and orientation of the graph. But wait, there's more! Remember earlier when I said when drawing out a graph, it's also good form to provide a table of values? You can do this through Desmos as well by clicking this button and this thing here and then, typing in some input values to which the table will then automatically make the output values. You may notice though that depending on what values you type in, your outputs might be huge numbers or small numbers or weird decimals that you wouldn't think of as much. So let's get a clean set of coordinates by taking advantage of the fact that the transformations do the same thing to every function they're in, so they affect their table values in a similar fashion as well. Let's start by going to a new line and making a coordinate with 2 parentheses instead of x and y values. On the left, we divide the parentheses by b and add h. On the right, we multiply the parenthesis by a and add k. Copy this coordinate about 5 times and then add 5 x values into the parentheses on the left and their corresponding y values from the parent function in the parentheses on the right. These points will now show up on the graph and automatically adjust based on your transformations, staying with the graph and allowing you to create beautiful 5-point tables by doing little more than just adjusting some sliders. Do ya love it yet? Do ya? As a reference, I will now do a little slideshow with each of the parent functions or math patterns that we looked at today, as well as their parent form table of values that can be put into the coordinates, its general form of the transformations, its graph, and its verbal description. You can screenshot these or copy them down to a notebook or whatever you do it is to study. I don't know how you do it these days. It's whatever. It's up to you. Just make sure you get them, because I guess these are notes. Really what you're going to want to learn for this is like how to use Desmos for all the graphing stuff. Outside of that, if the the concept of pictures moving around and doing wacky stuff, If that makes sense, then you know, whoop-de-doo. That's the whole point. Do a victory lap. You've earned it. And then when you're done, come back and do your homework.